Stefan Leichenauer, giving us a first lecture on black hole information and complementarity.
Okay. Thanks for inviting me and letting me give this set of introductory lectures to black hole information and complementarity. So this subject, has sort of a long history, but it's come up. It's in the news again as of about a year and a half ago. There were these, this paper about firewall, and I checked it a little while ago, and I think this paper has almost 150 citations already, and so it's sort of turning into a nice little subfield. So my goal for this set of 3 lectures is to, introduce some of the ideas behind black hole information and information loss and associated, paradox, together with the ideas of complementarity, which arose in the 90s to try and deal with the paradox associated with black hole information loss, and now the sort of newer versions of the old arguments, which have led to firewalls. And this is sort of a work in progress by the community. There is no consensus as of yet how the whole thing is going to turn out. And we'll see how far we get. I'll try to describe up to some of the cutting edge research. All right. So the plan for today is to talk about Hawking radiation and black hole information loss, and then I think by the end of today we should get to the sort of strong version of information loss paradox, namely the firewall argument as articulated by Amps in the paper from a year and a half ago. All right. So, and then tomorrow we'll continue, and I don't think I'll talk about complementarity today, and we'll save that mostly for tomorrow. All right. So first, some general comments about, some kind of cartoon comments about black holes and how we should think of them, and what they do. So what is a black hole? So we all know essentially what a black hole is, but let me just review. So here's a black hole. Okay, and classically, how does a black hole behave? Well, classically, a black hole, when you throw something in, we like to say that it gets eaten up. You throw in some matter, it gets eaten up. But really, that's not totally true. So if we're looking at a black hole from the outside, and you look at all the matter that's ever been tossed in, it sort of gets pancaked on the horizon. Okay. So this circle is supposed to represent the black hole horizon. And for those of you who are familiar with Penrose diagrams, it's also easy to see. If you don't know a lot about Penrose diagrams, it doesn't matter. I'm not going to use them heavily, at least not today. So the way it works on a Penrose diagram, here's the singularity and here's the horizon, and here's some matter, which fell into the black hole. But from the point of view of someone who's say here on the outside, that's you. You look at the black hole. You see what you can see. Here's your past light cone, and you can see all this matter. And as you go further toward the future, this point is sort of your future infinity. If you stay outside of the black hole, your past light cone kind of approaches the horizon, but it always, you always see sort of a cross section of matter just before it crosses the horizon. Okay, and that's sort of this stuff here. So you get a lot of stuff just sitting at the horizon from your point of view. And there's redshift factors and whatever associated with this, so it'd be hard to actually see. But the picture that this leads to, at least in my heuristic cartoon narration, is, what if you tried in, this classical picture to assign some kind of entropy to the black hole, okay? So you could, even at fixed mass, you could pile up all kinds of random stuff here in sort of an infinite number of ways. And it sort of suggests that classically, because of all this stuff hovering near the horizon, black hole entropy looks infinite. Okay, it's just this sort of, universal dumpster where you can throw anything you want into it. Okay, and you can try to regulate things by introducing some kind of cutoff, and sort of similar to the arguments that were given yesterday in Ninda's lectures. You might say that since all this stuff is piling up on the horizon, it sort of looks like the entropy should be proportional to the area, but then there's kind of an infinite constant, at least classically. And when we include quantum mechanics, or when we include quantum gravity effects, this infinite constant gets modified. Okay, basically there's a finite amount of resolution you can have. Namely, it doesn't make sense to talk about distances and area elements smaller than Planck size. So it introduces kind of a natural cutoff. So in this way of thinking about it, what quantum effects do is they regulate this infinite constant to a finite constant. 4 times L Planck squared. Okay, so we find that once including quantum effects, the entropy of a black hole is actually finite, and it's proportional to the area. Okay. All right. So far, so good. So now this is not classically. This is quantum mechanically. Black hole entropy is finite. All right. So black hole has finite entropy, and it has finite energy. It has some energy. The mass of the black hole. Okay. And the area is the radius, which is 2gn times 4 pi. So I'm working in 3 plus 1 dimensions. So the area, 4 pi r squared, okay? Energy, m, okay? So you've got some kind of entropy-energy relationship, okay? First law of thermodynamics is obeyed by black holes, so black holes have temperature, okay? Temperature is dEs, and you plug in these kinds of relationships, and you find we can express it in a couple different ways. I'll insert the explicit factors of the Planck mass, A pi m, or this is just 1 over 4 pi times the Schwarzschild radius. Okay, so black holes have a temperature, and in fact, black holes are quite cold for their size. Okay, a black hole, you should think of it in the same way that you think of a star, except a star, the temperature of a star is so hot that the typical wavelengths that come out of like the sun are much smaller than the size of the sun itself. Okay, whereas for a black hole, the temperature, so the typical wavelengths, are of order the size of the black hole, and in fact they're even smaller because of this kind of 4 pi. and I'll keep track of 4 pi's in this kind of thermodynamic discussion because they tend to add up sometimes. Okay, so the way you should think of a black hole is you should think of it as something as like a star with a finite amount of entropy that's very cold compared to its size. Okay.
This is a little bit of a postmodern view of black hole thermodynamics, right? The original story.
Yeah.
So sort of the opposite, right?
Yeah.
The entropy looks to be 0 because of no Herd theorems, but you find that the horizons have a temperature, so they have to have an entropy.
I'm doing things a little bit backwards, but I think I'm doing things a little backwards. So well, historically speaking, I'm not exactly sure how Bekenstein did things, but what you could do is you could do something like first calculate the temperature based on calculations, which I'm going to go through in a little while about Hawking radiation, and then kind of run backwards to figure out what the entropy has to be, and see that it's this. And well, the sort of funny thing about, and then the thing which is sort of extra funny is that if you had come from the point of view that the black hole entropy should be 0, classically, and then I showed you this formula, and then you try to take the classical limit, it becomes infinite. The L Planck goes to 0, the area goes. So the classical limit black hole entropy, sort of the correct point of view, is that it's actually infinite. And then I come up with this picture to try and justify that. But I run through it this way. Just I think it's nice. All right. So what's the picture? So the picture is we have our black hole, and we understand, quantum mechanically it radiates. So here's some radiation coming off of the black hole. And if we wait a very long time, eventually the black hole will be gone. It has a finite amount of energy. Eventually it radiates everything away, and will just be sort of the outgoing radiation left over, no black hole. So how long do we have to wait? Well, again, we can do a thermodynamic estimate of that. I said you should think of a black hole like a star. How quickly, so how long? Let's call this T evaporation. How long does it take to evaporate? So we just have to integrate, the energy loss rate the energy loss rate for the entire energy of the black hole. And the energy loss, now this is just approximate. There's a correct way to do this, which requires significant calculation. I invite you to read papers from the 70s by Don Page about how to do this correctly. But if we just want an estimate, we can use Stefan-Boltzmann Law, which says that the rate of energy loss by some black body is just temperature to the 4th times the area. So the area, 4 pi r squared times temperature to the 4th inverse. Okay, and then I can express these quantities here using these formulas in terms of the mass, well, which is the same as the energy, and then do this integral. Okay, and I will skip the algebra, but it's useful. This is one of those cases where it's useful to keep track of the 4 pi's that show up, because of they add up. So you do the integral and you get 4/3, and then there's a 4 pi cubed, if I kept track of it correctly, and then there's an m cubed, and then if I put in the Planck units, m Planck to the 4th. Okay, it's a very long time indeed. Okay, so like I said, if you cared about numerical factors, they tend to get kind of large, right? This is like 10,000 or something, and then this m cubed in Planck units is also, it's a very big number. Okay, I should have probably written down like what it is for solar mass. Does anyone know what it is for solar mass black hole this time is? It's really long, like much longer than, you know.
So 10 to the 72nd, much bigger than the age of the
Yeah, much bigger than the age of the universe isn't even a blip. I mean, it's still large measured in units of the age of the universe. And like I said, this is approximate. This numerical factor was not correct up to order 1 issues because of this approximation. But you know, there's some number here. Okay. Good. So we have a black hole. We wait a long time, and it goes away. And then we can also put something in over here. How do we make the black hole? So the prehistory of the black hole, maybe some scattering, right, of some particles, maybe a bunch of them, maybe some kind of collapsing shell. Okay, came in, formed a black hole. The black hole evaporated, and then it ended up as just some kind of radiation. Right. So I put this whole thing together. It looks like some kind of standard scattering process with a really long-lived resonance. Okay, really long-lived, much longer than we're used to, at least for a macroscopic black hole. But nevertheless, it's some kind of scattering process. And in particular, we should be able to, at least in principle, if quantum gravity respects unitarity, there should be some kind of S matrix describing this scattering process from the beginning to the end. Okay. In particular, if I start with some kind of pure state of matter here, that's got a lot of energy coming together, but it's some kind of pure state. The final state of radiation after the black hole is gone is just conventional radiation. Is going to be in some pure state, which is some unitary transformation of what I started. Okay. So
you're not going to consider the scenario where there are remnants at the end of the evaporation.
No, I've assumed that there's no remnant. I've assumed there's no remnant. I think, well, let me assume that there's no remnant for now, and I can come back to the issue of remnants later. But I think the conventional story, so I'm going to the conventional story right now. The conventional story doesn't include remnants, but of course, every step of this we'll revisit when we run into trouble. So, okay. The whole process is some unitary scattering. Okay. Described by the quantum gravity S matrix. Okay. And in particular, I could have embedded this whole thing inside of some really large ADS space, and then the sort of time evolution would just be described by the CFT Hamiltonian, which is unitary. So that's sort of an argument that convinces most people that this is just some unitary process. Okay. So far, so good. The problem, okay, is without quantum gravity, it seems like it's really hard to calculate what this radiation is. We can try to do our best without using quantum gravity. So the reason why we can make any progress at all is because we have a semi-classical description of the black hole. So we can try to get some kind of semi-classical description of this radiation. Okay, the semi-classical description of the black hole is in terms of the Schwarzschild geometry. Okay, so the next step, and we sort of all know the answer to what comes out when you look at the Schwarzschild black hole, but I'm going to go through it anyway because I think it's important to kind of go through it once, and it it gets you thinking about things in the right way. So so how do we compute? Okay, so semi-classical answer. field theory, quantum field theory calculation in curved space-time. Where the particular curved space-time I'm going to take is the Schwarzschild black. Okay. And as we'll see, this alone gives you an answer for what the radiation should be. And actually, even before we do the calculation, we kind of know that the answer is going to be information loss. So information loss means, in this context, it means that you start with some kind of pure state here, but what you end up with out here, you can't reverse these arrows. Okay, you can't. Normally, if you have some kind of unitary process taking you from initial state to final state, you can just act with U dagger to get the initial state back. But because, as sort of was already mentioned, the sort of Schwarzschild black hole solution that we're going to be using to do the effective field theory, it's, these no-hair theorems say that all black holes are the same. So pretty much any calculation we do in a sort of Schwarzschild black hole background, it's not going to, as input, there's nothing to tell us how the black hole formed. Okay, because after it forms, there's sort of nothing left. So we kind of know that the answer is going to be information loss. But for the purposes of making future arguments, and because this is supposed to be, educational, we're going to go through it. Okay, we're going to go through how it works and how we should think about the effective field theory in the presence of a black hole, what the vacuum looks like, things like that. Okay, and I think that's going to take up most of the rest of today. So before I do that, let me just underline some key words here. So so this curved space-time, it's the semi-classical picture, okay, of the black hole, and we're using effective field theory in this semi-classical picture, and we're assuming some kind of unitarity, and we've also assumed that there's no remnant. Okay, these are sort of all key assumptions, which we may find cause to re-examine. All right. So before talking about the Schwarzschild geometry, we're going to do something simpler. Okay. The simpler thing we're going to discuss is we're going to discuss Rindler space. Rindler space is a little bit simpler, conceptually simpler. It has all of the salient features. Plus, as it turns out, Rindler space is the near horizon geometry of the Schwarzschild black hole. So we actually, it's actually very relevant. Okay. So, and I'm going to look at 1 + 1 dimensional Rindler space. All right. So what is Rindler space? Rindler space, you should think of it as a portion of Minkowski space. So here's a picture. This is 1 + 1 dimensional Minkowski space, and I'm going to use coordinates t. So t is this t is time, this t is temperature. There shouldn't be much confusion because I'm not going to use this t again for a while. So capital T is now time, and then capital X is space. Okay. And if I look at so here's the origin. Here's sort of the past and future light cone. This region out here, above this light cone and below this light cone, this is the right Rindler space, and this region out here is the left Rindler space. Okay, so this is. These regions features within the light cones we could also give names, but I'm not going to use them. So if we look at the right Rindler space, okay, we're going to write down some coordinates and a metric which covers only this right Rindler space, and then we could do the same thing for the left Rindler space, right? So before writing down some formulas, let's sort of draw some pictures. So why do we care about the what's some physical reason to care about the right Rindler space? So the right Rindler space is appropriate when you're talking about what an observer would see who has constant proper acceleration. Okay? So let me write down one such trajectory. So if you're over here and you've got some proper acceleration, so you start moving this way, but then you accelerate back in the other direction, there's your trajectory. Looks like that. It's a hyperbola which asymptotes to these two dotted lines. Okay? And here's another one. And here's another one. Okay. These are all trajectories of constant proper acceleration, and the ones that get closer to the horizon, this is the Rindler horizon. This is the past horizon, this is the future horizon. The ones that are closer to the horizon are the ones that have greater acceleration. So as I move this way, the acceleration goes down. Okay. So yeah. So in my Riddler coordinates, which I'm going to introduce in a second, these lines are going to be lines of fixed position. Okay. So if you're at fixed position, that means you're one of these guys. If you have fixed Rindler position, which is clearly not the same as fixed Minkowski position. And these things are not geodesics because they have constant acceleration. Okay? So these are lines of fixed position. What about lines of fixed time? Okay? Rindler time. How about Rindler time? So if you think about, what time, what should time translation look like for these accelerated observers? So, these observers with constant proper acceleration, it means their velocity is always changing. It's changing sort of at a constant rate. So they're kind of, at this point, maybe this guy is at rest, his forward vector is pointing up, his forward velocity, or two velocity in this case. And then a little while later, he's boosted in that direction. And a little while later, he's boosted even more. So advancing in time in the Rindler sense is just boosting more and more. Okay? So lines of constant time look like this. Lines of constant Rindler time look like this. Okay? And these lines are just the lines you would get, if you take the, it's the same lines you get when you take the sort of the x-axis and boost it with a Lorentz transformation. Sort of as we all know, the axes do this, right? When you Lorentz transform, when you boost. And so those are, this boost action gives you lines of constant time. And there's sort of an interesting thing that happens, which I'll mention, and it's not going to be too important, but it's useful. Well, yeah, it'll come up again later. But if I, here's a line of constant time. If I sort of extend it into the left Rindler wedge, it looks like this. And this is an earlier time on the right wedge, but if I sort of extend the axis, as sort of I know I should by the boosting logic, it looks like it's later, okay, on the left wedge. This means that, in the usual convention, if I think of time translation as kind of boosting like this on this wedge, okay, in this wedge, this is sort of forward time translation. That boost generator, that Hamiltonian, generates time translation this way on the left wedge. Okay, so if I drew in, so here's a left wedge constant position hyperbola, and if I drew sort of the direction of time translation sort of pushes me this way over here, and it pushes me this way over here. Okay, so that's just, it's mostly convention, but it's basically, if you look at this is the boost generator is acting as our Hamiltonian, okay, and the boost generator pushes points in space-time like this.